Okay, today we're going to be looking at a very special example. This example is special because it's the last example of the whole semester. I'll wait a little bit for the applause to die down a bit before we talk about this. But it's also special in another way. It's special in the sense that it brings together a number of different things we've talked about throughout the semester, particularly near the end. And those three things are the investigation of a PID controller, that is a controller with proportional, integral, and differential components. It brings together that with the sketching of root locus plots to understand how the poles are affected as we change different gain parameters in our controller. And it also brings into the picture the design aspects we've talked about for the control of dynamic response in terms of percent overshoot and settling time. So let's talk a little bit about our goal here on design first, and then we'll get into the aspects of the PID control and the root locus plots. So one criteria here is to have a percent overshoot which is less than 10%. When percent overshoot is exactly equal to 10%, this says that we need a damping ratio of 0.6. So in terms of that angle phi that we draw in our complex plane, which is the inverse cosine of zeta, that angle is 53 degrees. The other part, which is based on the settling time. The settling time, you might recall, for first or second order system is 4 times the time constant. And basically that says that's 4 over the magnitude of the dominant pole. So therefore, from this we see that our dominant pole in magnitude, if it is equal to 6 seconds, that would be 4 over TS, or 2/3. How does that influence how we move around on the complex plane? Well, one thing we have talked about a good bit of these semester is this wedge. This wedge, which is formed by drawing at the angle phi, which in this case is 53 degrees, and then on the right hand side it's bounded by our constraint on the time constant. So in this case this line would be at 2/3. So what this means is that we have this truncated wedge, and in this wedge is where we need to be if we want to satisfy both the constraints on percent overshoot and on the time constant. Okay, now let's get to the PID part. For the PID controller, again, P is for proportional, I for integral, D for a derivative. The proportional, the transfer function is a Kp. For integral, it's the gain Ki divided by S, because that's an integration. And then for the derivative, it's Kd gain times S, where S is for the differentiation. If we put this group of 3 terms together over a common denominator of S, as we've done before, we end up with this. So in the end, the open loop transfer function is just that fraction GC times our plant GP, which is given above. So our closed loop characteristic equation we know is 1 plus GC times GP. So that's the function from which we look for our closed loop poles. We're going to look at 3 cases individually. One is just strictly proportional control. So if we come up to our KD, set that equal to a 0, Ki set that equal to a 0, our closed loop characteristic equation looks like this. With this, our closed loop system has 2 real open loop poles. Those open loop poles are minus 0.5, and minus 2. And no open loop zeros. So we'll keep that in mind when we look at the example in more depth. Considering now that the PI, basically setting KD equal to a 0, we get this. Now what we need to do here is what we're going to do, I should say first, is we're going to hold KP fixed, our proportional gain, and we're going to vary KI to see what influence that has on the poles. So first thing I need to do is get this in a form where KI is that gain factor which is out in front. So to do so, I'm going to multiply through by this and this, which then gives that. Keep in mind there's a 0 here on the left-hand side. And then so that we can isolate out KP, what I'm going to do is divide by everything else which doesn't involve the KI, and that ends up giving us this. So we have a numerator N of 4, a denominator D, where the denominator D is different than the proportional control in that we have added an additional open loop pole, S equal to a 0, as well as we have changed the two existing poles because we now have added on this a stiffness-like term here of 4 kp. Finally, if we look at PID, which is proportional plus integral plus a derivative, we go back to our general expression. And again, what I want to do is hold KP and KI fixed and have KD being our control gain. So same process, I bring this over by multiplying through both sides by that. Remembering the left side is a 0, we get this. And now to expose KD as being our control gain, I basically divide through by the sum of it, every term except that one, and so that process gives us this. So we see, and maybe we've talked about this before, is that what we have done with adding on the D part of PID, we have now added two open loops as zeros that are at the origin. And importantly, what we have done is, because of this term right here, we have moved one of the open loop poles away from the origin. So don't expect to have an open loop pole at the origin for this, but we do have now two open loop zeros at the origin. Okay, so what we are going to do here in this video is just look at the proportional control, and then I'll defer the PI and the PID controller to the next two videos. Okay, root locus. Let's do that first before we talk about design. So what we have here is this for our closed loop characteristic equation. I can alternately write this as a 0 is equal to s squared plus 2.5s plus 1 plus 4 times our gain kp. This is a second order characteristic equation. Put it in our standard form with a 1 in front of the s squared, this term becomes omega n squared, and this is 2 zeta omega n. The only one of the three where we're going to clearly be able to see where zeta and omega n come into play. Okay, as we look at it and go through our different rules and guides here, P1 and P2 are two poles. These are the open loop poles. Those are the open loop poles of our plant, and I've shown those with the red axis there in the picture. Where on the real axis does the root locus exist? We know it has to be to the left of an odd number of open loops, zeros and poles. So therefore, if I call this P1, which I guess I called that up there, and then P2 is this one here, on the real axis it's going to be between P1 and P2, where P1 is a minus 0.5 and P2 is a minus 2. So if I bring down my red line here, what I'm showing here is that's where the root locus needs to be when we're looking at the real axis. The breakaway re-entry points, do the calculations, and you'll find that you have one breakaway point, and that's at minus 1.25. So that's going to be somewhere in here. I'm not too worried about the scale. I'm just getting the trends here in the picture. Being that we have fewer open loops zeros than we do open loop poles, in fact 2, we have to look for 2 asymptotes. If you use the calculations, the equation that we have, we find that the intercept is at minus 1.25, the same place where the breakaway point is. And the 2 asymptotes, theta 1 and theta 2, are going to be plus and minus 90 degrees. So two things, or one thing that we see from these 2 results is that the breakaway points and the asymptotes become one and the same. That is not always the case. So I'm going to put my dashed line here at the minus 1.25. And again, we know that's the breakaway point, and we know that that's the asymptote. Departure and arrival angles, well, that's non-applicable here. Non-applicable because we have no complex poles or zeros. No complex, should say open loop, poles and zeros. If you do Rule 8, you'll see that there's no value of gain for which the root locus crosses over into the right half plane. So we put all this together. Again, our breakaway point and the location of our asymptotes is one and the same here at minus 1.25. So we see that our root locus goes to the right of P2. We knew that because it can't go to the left. It's got to go to the left of P1 because it can't go to the right. It breaks away here at S equal to minus 1.25, and so our root locus looks like this. So the comments that we have just based on the root locus itself is that proportional control effectively adds stiffness. This is what we've seen before on some other examples. And the result of this is that because it's changing the stiffness, when the poles become complex, that is when they have broken away from the real axis, it says that zeta omega n, which is equal to 1.25, is a constant. So we're actually rediscovering some results we've seen from before. Before we just looked at this as being a quadratic equation. We knew the answer, but root locus, we're not solving any equations, and we ended up with that same result. And that result is that the root locus, when they're complex, are straight line. Root locus, which is parallel to the imaginary axis, as expected. So in terms of design, recall our truncated wedge. I have a picture of this. I'm going to slide up here. We know that this was going to be at minus 0.667, so that's slightly to the right of P1. So what this says is that our poles, let me do this in, let's say, green. It says that as we increase our KP, when we're in this range right here, I'll cross hatch this. When it's in there, it satisfies our criteria. So again, what we've done here is we have looked at the three cases, P, PI, and PID control, get the general form, and we've applied that general form first to the proportional control. We drew our truncated wedge, which gives us our design space in the complex plane that satisfies the percent overshoot criteria and our settling time constraint.